So if you look, we never dealt with numbers over there. But we can also handle these continuous attributes also in the decision tree. Apart from categorical, numbers also can be treated with the decision tree. But then for the numbers, you need to, sorry, for the numbers, you need to find a specific threshold to divide the numbers. Like if we have a weight as one of the attributes in the data set, then you have to divide the weight with respect to some threshold. So there are many ways by which you can, there are many ways by which you can find the best threshold to devise the continuous attribute. And but I will not discuss that in detail. Okay. So, but handling the continuous, these are some of the problems in the classification. So many times when you construct a decision tree, it may be overfitting will occur. So overfitting is the circumstances in which the decision tree or the classification algorithm will work perfectly for the training set. But when we give testing data, the classification algorithm may not work properly. So that's why good accuracy on training data, but poor on the testing data. This problem is known as overfitting. And there are two methods or approaches that we can follow to avoid this overfitting. First is nothing but pre-pruning, and second is nothing but post-pruning. So in pre-pruning, what you can construct off a tree, and it is very difficult to decide when to halt the construction of the tree. So we don't know what will happen subsequently. What will happen will some point of time we have to halt the tree, and we have to check whether this problem, overfitting problem, is being avoided there. Second, we have this post-pruning. What we can do in the post-pruning, construct the tree completely and remove the branches or the subtrees from the fully grown tree. The two methods. One is that somewhere in the construction you have to halt the tree construction before it reaches the final stage. And second approach is that construct the tree completely and remove some of the branches or some of the subtrees from the fully grown tree. So these are two methods which will avoid this overfitting problem in the classification. And apart from this, these are some of the issues that we'll face in the construction of a decision tree. We also have many advantages of using the decision tree. One of the advantages which I've said earlier is that I said the decision tree is very good in accuracy. If you compare the many classification algorithm available across, the decision tree is able to give much high accuracy than the other classification algorithm. And apart from that, this decision tree is able to provide some simple understandable rules. We have discussed already. Whenever in the decision tree you will travel from the root to the leaf node, you will always come up with the rule. So the rule is very, very important, and it works well. This class decision tree, it's working well for the most of the problems. As I said, it can handle both the numerical variable and the categorical variable, and it can work well for both small data set as well as for the large data set. And the decision tree is able to provide a definite clue of which of the features are more useful for the classification. This is a very, very important point. If we take in the machine learning, one of the main important research problem is the feature engineering. Given in data set, which feature is most important for a given problem. So not, we can say, if you have a data set, you cannot declare this feature is important for all the problems. For each and every problem, the feature set will differ. And among the feature, which are the features are most important feature, to rank it, to identify the features from the data set which is relevant for the problem itself a big research task. It's called as a feature engineering. So this decision tree is helping us to find out which of the features are most important for the given data set. For example, morning you have dealt with the placement data set. Okay, so that is a very small data set. In general, the machine learning algorithm will be dealt with data size where the number of features will be more than 100, and the size of the data sets will be in TB or MB. It will be huge size. In those circumstances, for a given problem, to find out the very relevant feature for the given problem is very, very difficult. That's a very important task in feature engineering. In machine learning, feature engineering is a very, very important part. For example, take morning discussed problem, placement problem. So if we ask you, what is the important feature among all the four attributes which is given, how will you find out? Before you know the decision tree, will not know. You will be clueless to confirm which is a very important feature. But this decision tree will definitely give you a clue, or it will give a hint on deciding which is the important feature for determining the solution for the problem. For example, in the morning part, we have discussed, right? We have CGPA, communication, aptitude, programming skills. 4 features are there for the class variable. So in that, if you want to rank the variables according to this importance, you can always go with aptitude as a first rank, communication as a second rank. How I have marked aptitude as a first rank? Because as a first root node of the tree. So you can similarly mark the second high important feature is nothing but communication. What is the third important feature? CGPI programming skill. We have constructed the decision tree in the morning, right? So similarly, you can rank the features in the order of the information gain. Like aptitude is the first one, second one is the communication. In the order of construction of the root node, you can order the features and that ranks the importance of the features. So it is a very important point to note down the decision tree. If somewhere you want to find out which is the important feature for the given problem, so this will give you a clue, idea, because otherwise you will know where to start to find out the important features for the given problem or a given data set. So this will be a best start with the decision tree and to find the important features is the best way. Second, of course, though it has some of the advantages, many of the advantages, it has some of the weakness also. The decision tree models are often biased towards the futures having more number of possible values. So if we look into the construction of decision tree, so it will often bias towards the future or the attributes which have more number of possible values. Okay, so if your future contains more number of possible values, imagine that I have a future called programming ranking. So the ranking will be in the scale of 1 to 10 for all the participants. So that have 10 different divisions, right? So then decision tree will be likely biased to a future which is having more number of possible values. Okay, and as I said, this model may get overfitted or it may be underfitted quite easily. I have discussed already what is overfitted, and decision tree can prone to errors in classification problem with many classes and relatively small number of training examples. And a decision tree can be computationally very expensive to train. The training part, it will be time consuming. The decision tree, the data set is very large, it will be time consuming. So how we are going to, now we have discussed in detail about the working of the algorithm. We're going to see how we can able to evaluate the decision trees. So as I said, you have the accuracy is number of correct classification divided by total number of test cases. And one more important point is that this decision tree can also able to handle noise and missing values. Imagine that you have a data set which contains missing values and it contains noise also. So decision tree will able to handle this data which having the noise and the missing values, and in spite of that, it can able to construct the proper decision tree. That's one of the advantages, and it is scalable. So efficiently in a disk resistant database is very scalable, and it is interruptibility and compactness of the model. So all are the things, some of the advantages of decision tree, and this is something called holdout set, and is important. So the available data. This will, how will you divide the data set into training and testing phase? I will not discuss this in detail. And if you have the data set of a very small size, then of course, if data set size is very small, then you cannot able to construct a good tree. You have a reasonable size. The data set size is very small. You can have this N4 cross validation and leave one node cross validation validation test. I will not deal with that. And other evaluation metrics is nothing but precision and recall. You know, precision is nothing but true positive divided by true positive plus false positive, and recall is nothing but true positive divided by true positive plus false negative. And you have a F1 score for evaluation, which is nothing but 2 divided by the harmonic mean 1 by P plus 1 by R, and true positive rate and true false positive rate, sensitivity and specificity. So these are some of the evaluation metrics that will be used to evaluate how the decision tree has been functioning. Next, I will directly jump into this Adaboost, and we'll discuss in detail. Okay, so we have Adaboost is coming as the boosting algorithm, and okay, this is what the working of the Adaboost. So for this working of Adaboost, please make a note of the sample data set. Please make a note of it in a piece of paper so that while working out, it will be easy for us to understand. So I will give you some 2 to 3 minutes. In the meantime, can you please make a note of this data set? Am I audible?
Yes, sir.
Once you're done, let me know. I will discuss some of the theory parts, then I will go to the algorithm. Have I done?
Yes, sir.
Okay. Okay. So now we'll discuss. Okay. So now we'll discuss some of the ensemble methods. So we'll discuss through an example. So imagine that you are a movie director and you have made a short movie, and you want to really know the feedback of the movie. So what are the possible ways that you will get the feedback? So one of the possible ways that you may ask some of your friends to rate the movie. Other ways that you may ask 5 of your colleagues to rate a movie. Or otherwise you randomly choose some 50 peoples and then ask them to rate the movie. So if you look at this, all the three cases, point A and case A and case B, since you are dealing with your friends and colleagues, it may be biased, but if you look at the case 3, randomly if you choose 50 people, the feedback will be more generalized and diversified also. Okay, so these are the techniques that you'll have in the ensemble method. The ensemble method means you may club many of the classification algorithm, and the output of the many of the classification algorithm can be brought together as a single output for the given classification problem. So for example, one of the best ensemble model you can say is that with random forest. Random forest, what you can do is that I will discuss that random forest detail of the time permits. Otherwise, you will construct a different decision tree for the given problem. And if your test data will be given as input for the different decision trees, and you will check what is the output of all the decision tree. So if the output, whichever output is majority, that output will declare for the test data. So that comes under the max voting. So in the max voting is generally used for a classification problem. In this technique, multiple models are used to make prediction for each data point. So the prediction by each model are considered as a vote, and the prediction which you get from the majority of the models are used as a final prediction. So imagine that I have constructed, I have 3 classification algorithm, and these 3 classification algorithms are working on the placement data. So I want to know whether Thamare will get placed or not. What will happen? I have 3 classification model. Only what are the classification model? Logistic regression. You can use a SVM or you can use decision tree. Imagine that I have 3 classification algorithm. You give train or develop all these model. Give Thamare as an input for all these 3. So output, each one will give the output. So you will check which is the majority of the output. If 2 of the algorithms says a job will be offered, then we will declare job will be offered. If all the algorithms say job is not offered, you will say job is not offered. So we will go for maximum vote counting of the results. Based on the maximum count, we will declare the result. So this is an example. I will connect this with the movie rating. So if you see, you will ask 5 of your colleagues to rate the movie, and 3 of them rated at 4 and 2 of them rated as 5. So as I said, the maximum voting will be counted, and since 3 people are rated as 4, you will give the final rating of the movie as 4. Next, what you can do is that you can average it. So instead of going for majority voting, you can average it. So 5 people rated the movie, calculate the average of each and every score, and then give that as a final rating of the movie. Third one is nothing but weighted average. So imagine that you are choosing 5 people. Among that 5 people's, 2 people are movie critic who are working in the field of movie critic, who are working in a magazine, who will write critics about the movie which is released newly. So if those 2 people are involved in your sample, then what you have to do, you have to give some more weightage for the rating. because they are already experts in movie rating. So those people's remarks or those people's review marks should be considered seriously than the people who does not have an expertise in that area. So in those circumstances, you have to use weighted average. So in the weighted average, what you will do, you will assign weight for each and every people, and whoever having experience or expertise in the field, he will have a little upper weightage for them. So colleague 1 and colleague 2, imagine that they are a movie critic actually. So I will give an assign a little higher weightage than the other colleagues, 3, 4, and 5. So in that, the rating is given by the people. So what you will do is that you will multiply the weight with the rating, and they will come up with the average or final score of the movie. So for now, we discussed only the individual classifier, that how to build them and how to use them. We can also combine the multiple classification for the better results. Like one of the thing is nothing but bagging and boosting. So this bagging algorithm is nothing but bootstrap aggregating, shortly called as bagging. So given set D contains M training examples, grade essay of D by drawing N samples with the replacement. I will discuss that with an example. So in bagging, what will happen? You will create K bootstrap samples. So from the train data, you will create a K bootstrap sample like S1, S2, and Sk. So build a distinct classifier for each of the SI to produce K classifiers. For each of the samples, you divide the data into different samples. For each of these samples, you try to create a distinct classifier. Okay, what will happen? To produce you build a distinct classifier for each of the sample to produce Clay's classifier. Okay, either you can use same algorithm or different classification algorithm. So what will happen in testing phase? Classify each new instances booting of the Clay classifiers by equal weightage. So we'll see that. For example, you have a data set. Imagine that you have a data set from 1 to 8, and you can just shuffle this 1 to 8 in different orders, and that will be training set 1, training set 2, training set 3, and training set 4. And when this bagging helps, whenever the learner is unstable. So whenever learner is unstable, in the sense the small changes in the training set causes large change to the output classifier. And this is true for decision tree neural network. And it is not true for other K nearest neighbor, naive Bayes, and class association rules. Experimentally, if you see, the bagging can help substantially for unstable learners, may somewhat degrade the results for stable learners. So whenever you can say, whenever the data set is very small, and you want to somehow with a small data set you want to work. So in those circumstances, you can use this bagging. Whenever it is unstable, you can use it. This bagging will help us whenever the learner is unstable with a small data set. And a family of method is nothing but Adaboost that we're going to discuss in detail. The training here, what will produce a sequence of classifiers, and each classifier is dependent on the previous one and focus on previous ones here. The main important principle of this Adaboost is that you build a classifier. Okay. Each classifier is dependent on the previous one. You build a series of classifiers. First, you build a tree, and the second tree will be built on the first tree's error. In Adaboost, you will mainly concentrate on the error which is provided by the first classifier. If there is no classifier for the given problem, you will first construct a tree. And if you construct a tree, that tree will have some error. That error will be taken as a base for construction of the second decision tree. So this class, you please note the point, very, very important point. Each classifier is dependent on the previous one and focus on the previous one error. So examples that are incorrectly predicted in the previous classifier are given a higher weightage. But what here we'll do is that we'll build a classifier, and whenever the classifier is classifying the output wrongly, we'll concentrate on why the classifier is built, classifier has shown the classifier wrongly, and we'll try to work on only the wrong identified things. So incorrectly predicted classification will be focused here. So we will focus on the wrongly classified things, and we'll make sure that a perfect classification tree has been constructed. That's what the main principle about the Adaboost. We'll see that through an example how this error which is done by the decision tree has been focused on the subsequent decision trees. So how does Adaboost work? The actual performance of the boosting depends on the data and the base learner. It requires a base learner to be unstable as bagging, and boosting seems to be susceptible to noise. So should whenever there is a number of outline is very large, this Adaboost will not work. So have we noted down this problem? Have we noted this data set? Have we noted down? Can we go for the working?
Yes,
The principle is that Adaboost always works on the misclassified data. So we'll see how it works on the misclassified data. So imagine that we are going to deal with this data. I'm not giving all this data that I have shared already. So first thing is that we can construct a decision tree using the standard procedure. So if you construct a decision tree, the tree will be like this: blood circulation, and the left hand you have a pain, and right hand side we have a weight, and you have yes, no as to two different classification, and in the weight, if it is yes, then you have to check for block, and again block you have yes and no. This is the, imagine that this is a decision tree, which is a full set decision tree, which is constructed of 4 variables, which is given there: chest pain, good blood circulation, blocked arteries, and weight. As I said, this decision tree will always work on the stump. Stump is nothing but a portion of a decision tree is known as a stump. So imagine that chest pain, that is what our class label, that this is one of the feature in the data set. Chest pain is nothing but a feature in the data set. So this can be classified as yes or no. So this part is known as a stump. Shown below, this is a stump. We will use only, can only use one variable to make a decision. These stumps, these are called as stumps in Adaboost, and they are technically as a weak learners. We'll see why it is called as a weak learners. So this Adaboost, it will use the stumps, that is nothing but the weak learners. So in random forest, each tree will have equal weight and final classification. In contrast, in forest of stumps made with Adaboost, some stumps get more say in the final classification than the others. We'll look into that detail. So there are 3 main ideas about the Adaboost. The first point, to be notable point, is that the Adaboost combines a lot of weak learners to make the classification. So these weak learners are always known as stumps. Main point, as I said, it works on the misclassified data. That's why it's called as weak learners. So Adaboost combines a lot of weak learners to make the classification. These weak learners are always called as stumps. So stumps get more say in the classification than the others. The say is nothing but a technical term which has a formula in Adaboost that I will discuss in the due course of time. So some of the stump is nothing but a feature, and this classification is known as a stump. So some stumps get more say in the classification than the others. The third point is that each stump is made by taking the previous stump's mistake into account. So I'm taking this data set, and the first thing we do is to give each sample a weight that indicates the most important classification. Okay. The first thing we'll do in the Adaboost is that we'll assign a sample weight for each of the rows in the data set. The first thing is that we have to give a sample weight that indicates how important it is to be correctly classified. So at the beginning, now we are going to consider the data set we are given. So now we are going to assign a weight for the data set. So since it is a starting stage, we will assign equal weightage for each and every row in the data set. So how many number of rows are there in the data set? There are 8 rows. Am I right? There are 8 rows. So for this, each and every row in this data set, we'll assign a weight called sample weight. Since this is the beginning of construction of Adaboost, we'll assign equal weight for all of the rows. So we'll assign 1 by 8 for all of the rows. So how the sample weight be assigned is nothing but 1 divided by total number of samples. Here the sample size is 8. So it is nothing but 1 by 8. I am assigning a sample weight for each of the rows in the Adaboost. So this makes the sample of equal importance. All the rows will be taken as equal importance. So now, however, okay. So how to create the first step? So this is done by finding the variable. What are the variables that we have here in the data set? Chest pain, blocked arteries, and passion pain. We have 3 features, and the target variable is nothing but the heart disease. So we have to find the first system by looking at the variable chest pain, blocked arteries, or passion pain that contains the best job in classifying the samples. Now, if you look at the data set, all the samples have the equal weight. Since all the weights are same at first, we can ignore them. We start by seeing how well the chest pain classifies the sample. Look at the chest pain, and what are the 2 different values in the chest pain? Can you look into the data set and given? What are the values that is present in the chest pain? The chest pain
Yes
is
and no.
future, yes and no? Yes. Look, if the chest pain is yes, whether the heart disease is confirmed, check in the data set and tell me. If the chest pain is yes, whether the heart disease also yes, check. How many times it has given yes in the chest pain and how many times heart disease is also confirmed. Confirmed in the sense yes in the heart disease column. Look at the chest pain future and heart disease future that are not heart disease future, heart disease class variable. How many times if the chest pain is yes, if there is a heart disease problem, that is also yes.
3 times.
3 times. Check how many times if it is yes, it is no. Last 2 rows, 7 and 8 rows.
Yes, sir. 2, sir.
Yes.
Similarly, check for the if the chest pain is no, how many times the heart disease is also no. The chest pain is no. How many times there is no heart disease?
2.
2. Check how if the chest pain is no, how many times there is a heart disease? 1.
1.
Yes. Now we construct a stump for this. This is called a stump. This is how you can construct a stump. These are called weak learners. We'll decide which is the weak learner. Next, you you look at the blocked arteries. Look at the blocked arteries. The same thing you can do. Check how many times if there is a blocked arteries, there will be heart disease. There is a blocked arteries, heart disease is 3. And if there is a blocked arteries, how many times there is no heart disease? If there is a blocked arteries, how many times there is no
3.
3? Yes. And similarly in the blocked arteries, check how many times there is no blocked arteries and no heart disease.
1.
Yes.
1.
No blocked arteries and heart disease is yes. It is 1.
1.
So similarly, look at the patient weight. And when looking at the patient weight, I want to discuss something. So far now we have always dealt with the categorical variable. I said that we can also construct a decision tree with respect to the continuous variable. But look at the column of the patient variable, patient weight feature, sorry. Look at the column of the weight in the data set. That is numerical, continuous variable. Okay, while dealing with this numerical variable in the decision tree, you can always have a threshold value that I discussed already. So now the first time from the morning class, we are dealing with the numerical variable in the future set. So while dealing with the numerical variable, always you should have a threshold and you have to divide it. So now using how we can deal with the numerical variable, the same as how we can deal with the categorical variable. So I have just put a threshold here as 176, where the weight is greater than 176. How many of them weight is there are 2 classifications. The weight is greater than 176. How we get the 176 is nothing but with the help of the decision tree. Okay, so with the help of decision tree, we used to determine 176 for the best way to separate the patient. So this is the point where we can separate the weight. 176 is the threshold where we can bifurcate a tree, whether they will have heart disease or not heart disease. How it has been constructed using the same method which we discussed in the morning. So now, if you look into that, now check where are the weights we have greater than 176. What are the in the future patient weight? Look which are the weights are greater than 176. Row 1, row 2, and only 2 rows are greater than 176, right?
3 rows.
3 rows, yes. First, second, and third, yes. There are 3 rows which is greater than 176. Okay. If the weight is greater than 176, what is the probability that they have a heart disease? So 3, yes. So if the weight is greater than 176, you put yes in that column and the categorical as yes. So if the weight is greater than 176, you have heart disease for 3 people and incorrectly classified as 0. Am I right? Can I proceed? Similarly, check for the left hand side, right hand side. How many rows we have weight less than 176? There are 5 rows, right? Out of the 5, how many of them are correctly classified? 4 are correctly classified and 1 is incorrectly classified. Am I right?
Yes.
simple I can say is that in that column which has the continuous variable weight, whenever greater than 176 you put yes, whenever it is less than 176 you put no. Now we can easily able to find out the answer. So the first 3 columns in the weight will be yes. Rest of the values in the weight column will be no, because 1, 2, 3, 205, 180 and 210 it is yes. And after third row, remaining all rows from 4th to 8th, it is no, because it is less than 176, so no. So now check if the weight is no, and hard disk is also no. So 4 times it is correctly classified, 1 time it is incorrectly classified. Am I right?
Yes, sir.
Okay. So now this is how you have to calculate the sum, and from that you have to determine how to find out which is the weak sum that we have to use the formula called Gini index. So this Gini index, or we can call it as a Gini impurity, measures the degree or the probability of a particular variable being wrongly classified when it is randomly chosen. As I said, this Adaboost always work on the wrong classification. That's the main principle, underline the principle. So to find out the measures the degree of the wrongly classified when it is randomly chosen, we have to use a formula called Gini index. Gini index or Gini impurity measures the degree or the probability of a particular variable being wrongly classified when it is randomly chosen. So that the formula is given as 1 minus summation of I varies from 1 to n, PA of 2. Okay, PA is nothing but probability of an object being classified to a particular class. So this is the formula of Gini index. So now we can calculate the Gini index for this chest pain. So we will take each of these features and we'll calculate the Gini index. Like we did for the entropy and the information gain, we will calculate the Gini index because of the principle. Okay. So for already we found out how many, if the heart disease is yes, sorry, if the chest pain is yes, correctly classified is 3 by 5 probability, and if the chest pain is yes and incorrectly classified is 2 by 5. So if you calculate the Gini index for the chest pain and heart disease, yes, heart disease, it is nothing but 1 minus, apply the formula, summation of I varies from 1 to n, PF square. It's nothing but 3 by 5 the whole square by 2 by 5 the whole square. The Gini index, if you do the arithmetic, it will be 0.48 for the chest pain. Yes. I'm calculating the Gini index for the chest pain. Yes. Okay. Similarly, you have to calculate the chest pain. No. Okay. And with the chest pain is no, how many times it's been correctly classified? How many times it's been wrongly classified? So it is nothing but 2 by 3. Already we have done all these things here. You can do with it here. The chest pain is yes. Out of 5 times, it has been classified 3 times correctly, 2 times wrongly. If the chest pain, if the chest pain is no, 2 times it has been correctly classified, 1 time it has been incorrectly classified. The same thing you have to use. If the chest pain is no, correctly classified is 2 by 3, and chest pain is no, incorrectly classified is 1 by 3. Again, calculate the Gini index for the chest pain no. So we calculate, it will be, do the arithmetic, it will be 0.4422. So this is a Gini index for the chest pain no heart disease. Is it clear? Can I proceed?
Yes, sir.
Similarly, calculate the overall. Now we calculated the Gini index for chest pain yes and chest pain no. Now we have to calculate the Gini index for overall chest pain. Okay, so it will be nothing but overall how many times yes has occurred. Overall, you have 5 times yes out of the 8 columns. So 5 by 8 into what is the chest pain yes? What is the Gini index? 0.48. So 5 by 8 into 0.48 plus the overall data set. How many times the chest pain is no? 3 times. So 3 by divided by 8 into Gini index of chest no. No is nothing but 0.4422. So 3 by 8 into 0.4422. If you do the arithmetic, the Gini index of the chest pain will be 0.47. Is it right? Can I proceed?
Yes, sir.
Similarly, calculate the Gini index for the blocked arteries. Okay. So the blocked artery is yes, the correctly classified is 3 by 6. If the blocked artery is yes, incorrectly classified is 3 by 6. So calculate the blocked arteries Gini index for the blocked arteries yes. Apply the formula for the Gini index. It will be, do the arithmetic, it will be 0.5. Similarly, calculate the Gini index for blocked arteries no. If we do the arithmetic, it will be 0.5. So now we calculated blocked arteries, yes, Gini index, blocked arteries, no Gini index. So calculate the Gini index for the blocked arteries put together. So if you calculate, it will be out of the overall data set, you have 6 times yes, so 6 by 8 into Gini index of blocked arteries, yes. The Gini index of blocked arteries, yes, is 0.5. So 6 by 8 into 0.5 plus. And the overall data set, you have 2 times the blocked arteries, no. So 2 divided by 8 into Gini index of blocked artery, no. Gini index of blocked arteries, no. Heart disease is nothing but 0.5. So if we do the arithmetic, the Gini index of the blocked arteries is boiled down to be 0.5. Can I proceed? Similarly, you have to calculate the Gini index for the patient weight. So if you calculate the Gini index for the patient weight, yes, and Gini index for the patient weight, no, you have to calculate. And you have to calculate the overall Gini index for the weight greater than 176. So if we repeat the same step as a detailed above, you will find the Gini index of the weight greater than 176. It will be 0.2. So now for all the futures, we have found out the Gini index. The Gini index for the chest pain is 0.47. Gini index for the blocked arteries is 0.5, and the Gini index for the this is Gini index for patient weight. Okay, this Gini index for the patient weight is 0.2. So from this, we can able to find which is having the lowest value. So the lowest value is nothing but Gini index for the patient weight. So this will be treated as a first stump, though this will be treated as a first stump in the forest. So now to determine the stump, we have used the Gini index formula. So whichever having the Gini index less from all the features, that will be choosing as a first stump. So this is the first stump. See, this is the first stump. So greater than 176. This is the first stump. So look at the first stump. I already said this Adaboost always work on wrongly classified data. So in this stump, how many errors it has been done? So look at the left hand side. So yes, heart disease correctly classified is 3. So it is not classified anything wrongly. But look at the right hand side. So here there is one misclassification. Am I right? Am I right, class? There is one misclassification in this stump. This is a stump we are going to focus as per the Gini index. Now in this stump, we are going to focus on the misclassification. That is wrongly classified data. So here we have one data which is wrongly classified. So this has to be focused now. Is it clear?
Yeah.
Yes. So now this stump has one error. So the total error of the stump is the sum of weights associated with the incorrectly classified sample. Thus, in this case, we have totally 8 samples. So 3 plus 0 plus 4 plus 1. We have 8 samples. Now, out of the 8 samples, we have only one misclassified data. So the total error in this stump is nothing but 1 by 8. So now we have to note, because all the sample weights are added to 1. Initially, if you remember that we have assigned a sample weight for each and every row. Since this is the beginning of the data set, we have assigned the equal weightage for each and every row. That is 1 by 8 we have assigned. So in the beginning, how we can assign a sample weight at the first step, 1 divided by total number of samples. We have totally 8 samples here. So the sample weight at the initial stage will be 1 divided by 8. So because all the samples have equal weight at the beginning, which will add up to 1, the total error will be always between 0 and 1. And it will be 0 for a perfect stump. The total error will be 0 for a perfect stump, and it will be 1 for a horrible stump. So we use this total error to determine the amount of say. So now we have to calculate the amount of say. So the total error for this stump is nothing but 1 by 8. That means incorrectly classified sample is nothing but 1. Total sample is 8. So 1 by 8 is the total stump, total error. From the total error, we have to calculate the amount of say. So the amount of say is calculated as formula 1 divided by 2 logarithm of 1 minus total error divided by the total error. In other words, we want to relate this amount of say, and if you want to relate the total error, both are inversely proportional. Like you have information gain and entropy are inversely proportional. Here the amount of say is inversely proportional to the total error. So now calculate the amount of say. Already we know the total error for this stump. This is the stump we are going to deal with that we found with the Gini index. So in this, the total error is nothing but 1 by 8. The misclassification is 1. Total sample is 8. So 1 by 8. So the amount of say, if we substitute the total error, it will be 1 by 2 logarithm of 1 minus 1 by 8 divided by 1 by 8. So if we simplify it, it boils down to 1 by 2 logarithm of 7. So the amount of say for the Persian weight greater than 176 is nothing but 0.97. Similarly, you have to calculate the amount of say for blocked arteries, and you have to calculate it for chest pain. So the amount of say for the chest pain will be, what is the total error for the chest pain? Can you tell me? chest pain, I will go to the stump. Chest pain, what is the total error? Yes. What is the total error for the chest pain? What is the total error for the blocked arteries? Can tell me? Can anyone tell me? What is the total error for the chest pain? Yes. Total error for the chest pain will be
3, sir.
yeah 3/8, and for blocked arteries it will be
4.
yes 4/8. Yes. For the total amount of say for the chest pain will be total error is 3/8. So you apply the formula for amount of say 1 divided by 2 logarithm of 1 minus total error divided by total error. The 3/8 is the error for chest pain. So 1 minus 3/8 divided by 3/8. If you do the arithmetic, it will be 0.11. The amount of say for the blocked arteries will be 1 by 2 logarithm of 1 minus total error by total error will be 4/8. If you do the calculation, it will be 1 by 2. It will be 0. Sorry, it will be 0. So the amount of save for the blocked arteries will be actually logarithm of 1. So logarithm of 1 is 0. So the amount of save for the blocked artery is 0. So now, we know that the sample weights for incorrectly classified sample has to be determine the amount of save. Okay. Now, what we can do is that we have to modify the weight for the incorrectly classified sample. So already we determined which is the stump you're going to deal with. This is a stump. How we finalize this is the stump? Using what metrics we finalize this is the stump that we are going to deal with? Among the weight, blocked arteries and chest pain, how we arrived at this weight? Based on Gini index. Okay. And so this is the stump which you're going to deal with. So when you create these terms, all of the sample weights are same, and this implies that we didn't emphasize the importance of incorrectly classified sample. But once we located the stump, now we have to focus only on the incorrectly classified sample. So for that, we need to change the sample weight now. Initially, the sample weight for that will be 1/8. So in this weight, which is the row? Can you tell me which is the row that is incorrectly classified in the weight column? So I have incorrectly classified as 1, right? So if the weight is greater than 176, no. Which is the incorrectly classified sample? Which row is incorrectly classified? Can you tell me? Class?
Row 8.
Which row? Tell me the row number.
Row 8.
No, sir. No. Row 8 is correctly classified. Because weight is less than 176. So it is no. No, and there is no hot disease. It is correctly classified. Which is the incorrectly classified sample I'm asking? In the no category.
Okay.
So number 2, row number.
No, row number 2 is correct because
Row 4.
yes, row 4 is the correct answer. Row 4 is the correct one. Row 4 is incorrectly classified sample. Okay. So now we have to focus only on that row because that is the incorrectly classified sample. We have to focus only on that. That is what Adaboost says. So this is the row. Stump greater than 176 incorrectly classified. The one sample is given below. The chest pain is yes, blocked arteries is yes, weight is 167, and heart disease is yes, and the sample weight is 1/8. Initially, we assigned equal weight for all the samples, so it is nothing but 1/8. So we will emphasize the need of the next term to correctly classify. So as I said, Adaboost always work on the incorrectly classified sample. So this is the incorrectly classified sample. Now we are going to work only on this data. So we have to make sure that these incorrectly classified data is classified correctly in the subsequent constructions of decision trees. So we will emphasize the need for the next term to correctly classify it by increasing the sample weight. How will you make sure that this incorrectly classified sample should be correctly classified? We have to increase the sample weight. How we can make sure that incorrectly classified sample should be subsequently classified as a correctly sample should be correctly classified? That will be done by adjusting the sample weight. So we will emphasize the need for the next term to correctly classify it by increasing its sample weight and decreasing the sample weight for all other rows. So this row alone, somehow we have to increase the sample weight. In other words, we have to give due importance for the incorrectly classified stump, and for giving the due importance for the incorrectly classified stump, we have to increase the sample weight. How will increase the sample weight? That is what the next question will be. Only if we increase the sample weight, we will be focusing on the incorrectly classified sample. But how we will increase the sample weight? Again, we have a formula for that. So let us proceed with increasing the sample weight for the incorrectly classified sample by the given formula. So the new sample weight is equal to sample weight into e to the power of amount of say. Already we have calculated the amount of say, right? For each of the things, we have calculated the amount of say. We have calculated the amount of say for all of the futures. So that we are going to use it now. So sample weight into e to the power of amount of say. So what is the sample weight for the given column which is incorrectly classified? Initial sample weight is nothing but 1 by 8. So 1 by 8 into e to the power of amount of say. Already we have calculated the amount of say for weight. What is the amount of say for a weight? Go to the amount of say which is already calculated for the weight. The amount of say for the weight greater than 176 is nothing but 0.97. Substitute the same here. So 1 by 8 into e to the power, the amount of say is nothing but 0.97. So if we calculate e to the power 0.97, it will be 2.64. So the new sample weight for the incorrectly classified sample is nothing but 0.33. So now this new sample weight should be substituted in the place of 1 by 8. Have you understood, class?
Yes, sir.
So now instead of I will take the same row which is incorrectly classified. So which is nothing but chest pain is yes, blocked arteries is yes, patient weight is 167 here, and heart disease is yes. And now the sample weight has been updated with the new sample weight. It's nothing but 0.33. Okay, good. Now to give importance for the incorrectly classified sample, we increase the sample weight. Once we increase the sample weight, it is our responsibility to decrease the other sample which is correctly classified. Okay. So again, how to decrease the sample weight for other rows which is correctly classified? Again, you have to use the new sample weight formula, but it's slightly different. The new formula to decrease is nothing but new sample weight is equal to sample weight into e to the power minus amount of say. Here we have amount of say for increasing it. For decreasing the sample weight for the other correctly classified rows, it is nothing but e to the power minus amount of say. Okay. So same thing. So 1 by 8 into e to the power amount of say. What is the amount of say for the weight future is nothing but 0.97. So 1 by 8 into 0.38 is nothing. Minus 0.7, it will be 0.838. So if you calculate the new sample weight, it will be 0.05. So this 0.05 will be substituted for rest of the correctly classified rows. See, for this incorrectly classified, we have given more weightage for sample weight. Okay. Rest of the things which is correctly classified, we have substituted the new sample weight by the formula 1 by sample weight into e to the power minus amount of say. If you do that, you will get 0.05. That 0.05 will be substituted for rest of the correctly classified. This correctly classified thing. Have you understood until now? So again, I'm emphasizing this Adaboost will work on the incorrectly classified data. Can I proceed?
Yes, sir.
So now if we calculate the new weight, so whenever you have a weight, it should be add up to 1. But if you see here, if you add all this new weight, it will not be add up to 1. So we have to normalize it. So new weight has been normalized. So, but if you look at the sample weight, if you sum up, it will be sum up to 1 actually. But the new weight is not summing up to 1. So we have to normalize it. So how we can normalize it? So we need to normalize the new sample. So it will add up to 1. If we add all the new sample weight, it is sum up to only 0.68. It is not summing up to 1. So in order to normalize it, we will divide each of the value by 0.68. So if you divide each of the every new weight by 0.68, you will get new normalized weight. It's nothing but 0.07, 0.07, 0.07. And the fourth row, which is incorrectly classified data, will get the 0.49. And the rest of the rows will get 0.07. Until then, it is clear?
Yes, sir.
Okay, good. So now we have this data set with new normalized weight. Okay. Chest pain, blocked arteries, patient weight, heart disease, and new normalized weight we have. So the normalized weight will be considered as a sample weight now. So since those are what we want on the next step. So now for considering the next step, we will not use this initial sample weight and new weight. We will only use this normalized weight. We understood? Okay. So So we'll proceed further. So in theory, we could see that we could use the sample weights to calculate the weighted Gini index to determine which variable should be split the next term. So initially to calculate which will form the stump, we use the Gini index formula. So now the weighted Gini index would put more emphasis on correctly classifying the one that was misclassified in the last term, since this is okay. So with the help of normalized weight, we will create a new data set. Now what we are going to do now, we are going to only focus on the incorrectly classified data. So this is the incorrectly classified data. Understood? So to work on this incorrectly classified data, now we are going to create a new data set. From the existing data set, we will create a new data set. How will we create a new data set? So with the help of normalized weight, we will create a new data set. This new data set will contain most probably the longly diagnosed records for its training purpose. How will you do that? How will you construct a new data set? That's one important step. So this is what the sample weight, right? For each and every row, we have 8 rows, and each of the row have a sample rate of 0.0. First row 0.07, second row 0.07, third row 0.07, and the fourth row, incorrectly classified data, we have weight as 0.49, and row 5 to 8 contain 0.07. Okay. So now what is the range here? It is nothing but 0 to 0.7. And second row range is nothing but 0.8 to 0.14, and the third row range will be 0.14 to 0.21, and the fourth row will be 0.22 to 0.71, and the fourth row will be 0.72 to 0.79, and here it will be 0.80. I mistakenly written as 0.78. It will be 0.80 to 0.86, and it should be this. It should be 0.80, right? You please correct this mistake. It should be 0.80 to 0.86, and it should be 0.87 to 0.93, and it should be 0.94 to 1. This is how we will split the range. Any doubts here? You have to now write the sample weights, and you have to write the range, cumulative range. Any doubts?
No, sir.
Okay. So now what is the rule is that you have to generate the random number. How many random numbers you have to generate? You have to generate 8 different random numbers. Okay. You have to generate the random numbers to construct a new data set of size. The data set, you have to construct a new data set, right? The data set size should be same as the old data set size. What is the old data set size? Old data set size is 8. Okay. So now you have to construct a new data set that should also contain 8 rows. Okay. For constructing a new data set, you have to generate 8 different random numbers. So the range in which you have to generate a random number is nothing but 0 to 1. From 0 to 1, you have to generate 8 different random numbers. So once you generate 8 different random numbers, you have to map that random number with the range. Imagine that the first random number which is generated is nothing but 0.53. So tell me 0.53 falls under which range? Class?
Row number 4.
Yes. If 0.53, then if 0.53, you have to check which row it falls under. It falls under 4th row. Now what will happen since it falls under this 4th, this range, we'll add this row 4 to this row 4 will be added to the new data set. What is the row 4? What is the row 4 data set? Row 4 will be nothing but, what is the row 4? Look at the original data set. What is the row 4? Yes, 167, yes. Am I right? Am I right, class?
Yes, sir. Yes.
Okay. Imagine that you have similarly generated 8 different random numbers. So if we generate 8 different random numbers from the range, we can easily find out which is having the higher probability to occur in the new data set, which row will have the higher probability to occur in the new data set. So you are generating a new data set. The new data set will be exactly the size of the original data set. Now we are going to generate random numbers in the range from 0 to 1. Okay. If you generate random numbers in the 0 to 1, if you generate a random number, each of the random number which is generated should be mapped with the range. Okay. So from the range, I'm asking a question to you. Which row will occur in the new data set with high probability?
Row number 4.
Yes. Why the row number 4 will occur with high probability?
Range is
very high. Since the range of the 4 is very high, there is a high probability that this row 4 will be added in the new data set many times than the other rows. This is what the core essence of this Adaboost algorithm. So if you may imagine that this will be the new data set for me, from the random number generated, this will be the new row. Look at the new data set. This is the new data set I got generated. So look at the new data set, check how many times this row 4 has been repeated. So it is the first time, second time, third time, 4 times the new row has been repeated. 4 times the new row has been repeated. Are we able to appreciate the concept? Why it has been repeated 4 times? Because the range of the row 4 is very large. And since the range is very large, the probability that random number will fall in the range is very high. That's why if we say look into the new data set, the row 4 is repeated 4 times. Same, this is for example, it may be repeated for 3 times, 5 times, 6 times also, maybe. For my generation, it is 4 times. Can you able to appreciate that?
Yes, sir.
So the random number generated may fall in some range. In that case, add particular, okay. So if you look carefully, row 2, 4, 5, 6 are repeated in the new data set. Okay. So this new data set is further used for Adaboost algorithm. So if you carefully note, the row which is wrongly classified is repeated many times in the new data set. If it repeated many times in the new data set, what will happen? That row will be trained many times. So the misclassification will be trained many times in the Adaboost algorithm so that it will be correctly classified. So the new data set is used further for this Adaboost algorithm. So lastly, we'll give as again we will construct like we will keep on going it, and whenever we found a stum and the stum misclassification will be viewed seriously, and we'll construct new data set until the incorrectly classified sample will be correctly classified. So lastly, we'll give all samples equal sample weight like before and assign a new sample weights all of the new data set. So again, we will try to find from the beginning. So now once this data set once we arrive at a new data set, again we will assign a new sample weight. So the sample weight will be 1 by 8 now. So for the new data set, again we'll assign the sample weight. Again we will work on a Gini index. Okay, again you will find out the amount of say. Again you will find out which is a misclassified data. Again you will construct a new data set. Okay, any doubts? Any doubts? Again, we'll go back from the beginning and trying to find the stum that does the best job classifying the new collection. This is how the errors that the first tree makes influence on the second tree is made, and the errors that the second tree makes influence the third tree is made. So now if you see, the second stump will be created on the error which is done by the first tree, the first stump. Any doubts? Hello?
Yes, sir.
So this is how you will construct. This is how we will construct the Adaboost. As I said, it mainly works on the misclassification of the data. Using the misclassification, using the error which is committed by the first term, that error will be taken into account and subsequent tree will be constructed. Can I go to the PPT? Now, if I redo this, you can able to understand. So it produces a sequence of classifier. Each classifier is dependent on the previous one and focus on the previous one's error. Example that are incorrectly predicted in the previous classifier are given a higher weightage. So now we can able to understand each of the sentences. And the actual performance of the boosting depends on the data and the baseliner. It requires the learner to be it requires the baseliner to be unstable as a bagging. Any doubts in this Adaboost algorithm? Any doubts?
No, sir.
So, Dr. Feroz, if there is a time, I will go through random forest. Otherwise, I will open the session for the question. Feroz, can you please suggest me?
Yes, sir. I guess we can move for some more time.
Okay, maybe around 10 minutes, 10 to 15 minutes.
Yes, sir. Yes, sir. Please.
Random forest. Okay. So here I have why random forest. Before you should know why we should go for random forest. Already we have Adaboost, we have decision tree. Why random forest? So in random forest there is no overfitting. We will not face the overfitting problem, and random forest is very good in accuracy, and it can work on the missing data. Okay. So these are the advantages that why you should go for random forest. So a random forest, or we can otherwise called as a random decision forest. It's a method that is operating by constructing multiple decision trees using the training phase, and the decision of majority of the trees is chosen by the random forest as the final decision. So imagine that I have a decision tree 1, I have decision tree 2, and I have decision tree 3. Now you know how to construct a decision tree. So I have constructed a decision tree for the problem to classify the fruits. And now I given an input, and the decision tree 1 classifies the input as apple, and the decision tree 2 classifies the input as a lemon, and the decision tree 3 classifies the input as an apple. Then the random forest clubs all this decision tree and will check the majority of the voting for each of the decision tree. Since we have 2 majority for the apple and 1 for lemon, we'll go with the final decision as apple. This is how the random forest works. A random forest is nothing but a collection of a decision tree. So this is how, imagine that in a basket you have 3 different fruits like apple, cherry, and orange. Okay. So now I'm going to classify these fruits. So if I'm deciding a diameter as a parameter, if the diameter is greater than or equal to 3, I'm segregating the fruits of apple and orange in one basket, and which is its diameter is not greater than or equal to 3, which is nothing but I'm segregating the fruits in one. It's nothing but cherries, but the right answer has to be further bifurcated. So again, I have to give some criteria. I'm checking whether the color is orange. If it is true, then I'll segregate the orange fruits in one basket. If it is false, I will put the non-orange fruit in another basket. So this is the final classification. You will see all the 3 baskets only containing the corresponding fruits. There is no any mixing up of fruits. This is how we will construct a decision tree. So each branch of the tree represents a possible decision, occurrence, or a reaction. Similarly, if we have 3 different fruits, like instead of cherry, if we have a grapes, again the diameters will work perfectly. So how does the random forest work? As I said, you again you have a basket which contains cherry, apple, and orange, and again you filter with diameter. And if you filter with diameter, cherry will go, and apple and orange will go in another basket. Filter with color, then we can segregate the food. This is the tree 1. The same problem can also be divided into, now we have filtered with diameter first instead of color. You can always use color as a first parameter. So if you choose color as a first parameter, then the color is red, then we will put cherries and apple in one basket, and the color red is false, we'll put oranges in another basket. Again, you can split the cherry and apple with respect to the shape. If it is circle, you will put it in one basket. If it is not circle, you will put it in another basket. So this is a second tree. This is the first tree. This is the second tree. Again, you can construct different trees. Third decision tree, how you can construct, we will check whether the diameter is equal to 1. The diameter is exactly 1, we will segregate as cherry, and if the diameter is not equal to 1, exactly, it will segregate in apple and orange in another basket. And then we have another parameter to check whether the fruits is grown in summer. If it is true, then we'll segregate orange in one basket and apple in another basket. If it is false, I will segregate orange in another basket. So we have now constructed 3 different decision trees, right? So now this is how the 3 different decision tree will look like. Tree 1, tree 2, and tree 3. So now imagine that you have a test data. You have a test data. So the test data color is not there. It is a missing value there. So you are given a fruit, but that you don't know the color of the fruit. You have a missing value. I already said that random forest algorithm will work for the data set which has the missing values. So here imagine that color is yes. So only these, this is the input that will be given. So if you give that as an input for all these things, for all of the 3 trees which I discussed, so the first tree will classify the given input as orange, and the second tree will classify the given input as cherry, and the third tree will classify the input as orange. So if you go for majority voting, then the output will be defined as an orange. This is how the random forest will work. I think I'm done with Dr. Feroz, and now the session is open for questions. Any question from the participants, you can please ask me. Dr. Feroz?
Yes, sir. Dear participants, your queries can be asked now, and you can put your question in the chat box also. I will read out for the resource person, if you have any.
Any questions? Coffee?
Yes, I have a question.
Yeah, please.
Yeah, I would like to know how you got the 176 as a threshold for the weight for classification. Please go over how you
Can
got
you
the 176.
can you please type in the chat box? Your accent uh, is not clear to me. Can you please type the same in the chat box? Hello. Can you please type the question in the chat box?
Okay.
In the meantime, other participants also please respond. If you have any questions, you please ask.
How we can use the GA in random forest? What is a GA? Dr. Soman Kankar, what is GA? Okay, how we can use GA in random forest?
That is
So,
genetics.
I'm not sure about the application of genetic algorithm in random forest. In specific, if you have any doubts in details about the random forest or Adaboost or decision tree, I will be happy to answer. Application, I'm not sure. I have not done any experiment on that, so I'm not sure about that. Okay, please go over how you get 176 threshold value. Yes. So for this question, I have already answered. For the construction of the decision tree in the morning section, we have only looked at the categorical variables. We never dealt with the numerical variables. So in the numerical variable, if you dealt with the construction of decision tree, you have to fix your threshold as 176. So that I have discussed. I have not discussed that in detail. You can always we have to follow a set of procedures for the numerical value. For the continuous variable, you have to follow a set of procedures. This is much alike as a categorical variable, and you can fix the threshold as 176, which is the best way for classifying the hard disease as yes or no. So you have to work for a set of procedures that I have not discussed in this class. Only for the categorical variable I have discussed. If you go to the morning example, all the 4 variables which have dealt with the placement data, which are categorical variables like CGPA, communication, aptitude, and programming skills. If we have categorical variable, if we have the continuous variable, we can always deal with we can deal with the continuous variable also in the construct of decision trees. That is possible. That we have to fix a threshold, like how we did for this 176 in the hard disease problem for the Adaboost. I have given one slide I might not discuss in detail due to lack of time constraint, but there is a set of procedures. If you want, I can share you that. I hope, is it okay? Coffee?
Yes, sir.
Yes.
Okay.
Again, it will take more than half an hour to discuss if we take the continuous variable as one of the features in the decision tree, it will take another half an hour. So due to lack of constraints, I'm not dealt with that.
Probably, sir, we can discuss that in our next training program if you join again.
Yeah, sure. Any other questions?
Participants, do you have any more questions? Otherwise, we will wind up today's program. So, all right, as I mentioned, you can put your queries later in the Telegram group also. I'll communicate to the resource person.
I will drop my email ID in the chat box. If you have any further questions, you can drop an email to me. I'll be very happy to solve. If I know, I will solve it.
So, all right, guys, please note down the email ID, and you can contact Dr. Thiyagarajan directly with your queries. So thank you so much. In fact,
I have to say that this was the most interactive session so far we have seen, and it was most entertaining also for all of us. So thank you so much for joining as a resource person. I hope the participants also have enjoyed. So please put your feedback in the feedback form which is being shared in the chat box. Dr. Thiyagarajan, thank you for joining again as a resource person in the second phase also. As I mentioned, please join as a resource person in the third phase as well. So
thank you, Dr. Feroz, and thank you for inviting me again and again. I'm really honored to be there, and it's a good session. And thank you so much for the participant for the patient listening. And if you have doubts in future also regarding this, please feel free to drop an email to me. I will be happy to help you out in this thing.
yes,
Thank you, Dr. Feroz.
Okay, sir. So you'll be sharing the PPT because
I will be sharing only the PPT, not the working outs. I will be sharing the PPT for sure.
all right, sir. All right, sir. All right. Okay. So, dear participants, the PPT will be shared through the Telegram channel. So, thank you so much for joining today's session. Thank you, resource person, Dr. Thiyagarajan, once again. So, dear participants, so today's session we are officially winding up. So, tomorrow morning again we'll be starting the program exactly at 10 o'clock. So, please try to join exactly at 10 o'clock or 5 minutes before. Okay, so it will be more appreciable. So thank you so much once again.
Thank you all. Thank you so much. Bye.
You may
Thank
leave
you.
now. Okay. Bye bye all. So we'll meet again tomorrow morning.